In this lesson, we cover equations with variables on both sides. The learning intentions are to solve linear equations that have variables on both sides, identify special solutions of linear equations, and use linear equations to solve real-life problems. So in this example, we're to solve noting that the value or variable of p exists on both sides of the equation, so we will combine them using inverse operations. So the first order of business will take this negative 3p and combine it with the 5p on the left using its additive inverse of positive 3p. And that leaves us on the left-hand side with the sum of 5 and 3p, which is 8p, and on the right-hand side with 24. So now we could divide both sides by p's coefficient of 8, and that gives us finally the p value of 24 divided by 8, which is 3. In this example, we have two pairs of grouping symbols on both sides, each containing a copy of our variable. But one important thing that I want to note is on the right-hand side here, we have a decimal. Now with algebra and beyond, you want to convert that to a fraction. So on the left-hand side, I'll do some distribution, but on the right-hand side, the only thing I want to change is that 0.5 to a 1/2. So on the left, I will multiply the value of 2 to each term inside of the parentheses. And what that results in is the following. 2 times 3n is 6n. And then again, back to the 2. Now this time times the 2 times the negative 4. So a positive times a negative is a negative. Handle the sign first. And then 2 times 4, which is 8. I carry on with the rest of the problem. Onto the other side, I replace that 0.5 as a 1/2 times that quantity of 10 minus n. Now I have a choice. I could distribute that fraction to each term, but then I'll have a fraction in front of my variable, and that will just make it a little bit harder because I'm dealing with mixed numbers. So instead, what I'm going to do is a nice trick where instead of making the problem more complicated by bringing more fractions throughout the problem, I'm going to multiply everything by 2. So on the right-hand side, I will multiply by 2. And on the left-hand side, I will multiply by 2. Because what you do to one side of the equation, you could do to the other. So use your creativity to make the problem as easy as you can. So on the left-hand side, I now will distribute this 2. So 2 times 6n is 12n, times negative 8 is negative 16. On the right-hand side, I am going to simplify 2 divided by 2. So by choice of multiplying by 2, a 1/2, you just get the multiplicative identity element of the set of real numbers, which is 1. So now I don't need those grouping symbols anymore because it's just a 1 on the outside. So I could simply have it as 10 minus n. Now these numbers are integers, so they're a lot easier to compute with. And so like in the previous problem, I will take terms and combine them. And here I will use the additive inverse of n, which is positive n. And also I'm going to bring that negative 16 from the left to the right as a positive 16 to join with that 10. Simplifying, I have on the left 12n plus n, which is 13n. And on the right-hand side, the sum of 16 and 10, or 26. And finally, when I divide both sides by 13, we arrive at the answer for n of 2. So notice the numbers were easier to work with when we use this trick of instead of distributing a 1/2, instead we just multiplied both sides by the denominator, and that way the fraction simplified to 1. In the next part of the lesson, we will identify special solutions of linear equations. So what that looks like is normally you have one solution like you see here, where you have a variable on one side, isolated by itself, and then on the other side you have a number. That's the value of the variable, and that's the end of the story. Now, that's not always the case because sometimes an equation is set up and it represents infinitely many solutions. So At some point in the equation, you'll see that both sides are the same thing and they equal one another always. In this example, I show that the constant of 5 is equal to itself all the time. Now, sometimes if you see, for example, that when you're simplifying, you get like 3x minus 1 on the left-hand side, and you look to the other side of the equation and spot the same thing, well, that's always going to be true. And when you simplify it, you'll get 0 equals 0. So you could stop early at the reflexive property when you see mirror images on both sides, and you could just say, okay, I'm going to have infinitely many solutions. Now, no solution is when the answer makes no sense. Like in this case, we're looking at when the constant of 7 would be equal to 4, and that's never true. So really we use the not equal symbol here. And then for the whole answer to the problem, we say no solution. So we're going to take a leap forward, and instead of just always having a variable equals a number in the end for us to box, we might have to use the words infinitely many solutions, and we might also have to conclude that to the original equation, it was not set up in a way that describes a real true relationship, therefore there's no solution to that equation. Let's do some practice. We are going to solve, and in doing so, I could distribute that 4 or realize on the right-hand side that 12 is a multiple of 4, so I'm just going to divide both sides by 4. And on the left, we get 3d minus 1. On the right-hand side, 12 on 4, or 3d. Ah, look at that. So notice on the left-hand side, I have a 3d minus 1, and on the right-hand side, I just have a 3d. That equation is not balanced. So I know right now that there's not going to be a solution. So I could stop here and just say the null set symbol and box it, or I could use the words no solution and then box that. The choice is yours. Make sure with the null set symbol that you go from upper right to lower left with that slash. Now, to show you how this is the correct conclusion, I will go ahead and do the rest of the algebra, which is not necessary, but I'll do that to combine the like terms with the variable d, and then I'll move the constant to the other side. And so on the left, 3d minus 3d is nothing. And then on the right-hand side, 1, and that's never true. So that's where we get our no solution. Let's try this example. Again, I notice everything is a multiple of 7. So instead of distributing through, I'm going to divide by 7. Now be very careful when you do this because this 7 has to go into each term. So every quantity in every part of the equation has to be treated the same or equal. So I'm going to divide that 7 into 21 and get 3, and into the negative 7 and get negative 1w, or just negative w. On the right-hand side, the 7's divide out. I don't have a need for the parentheses anymore, so I just write 3 minus w, and voila! That is an always true statement. So I could answer right now that this is infinitely many solutions, meaning no matter what, so lots of right, so there it is. And I would box that as my final answer. Or our abbreviation can be the infinity symbol. Now, we have infinitely many solutions because no matter what value you would put into w on either side, you can ensure that you will always have equality. Modeling with mathematics is how we are going to conclude this lesson. Taking a look at this example, we see that Serena bikes for 3 hours to reach her favorite beach. She bikes 2 miles per hour faster on the way back. So the trip back takes only 2.5 hours. How fast did she bike going to the beach? What we really need to realize in this problem to solve it is that the distance to the beach is the same as the distance home from the beach. And remember, anytime that you're going to deal with distance and speed and time, you're going to use that formula of dirt, d equals rate times time. So the distance to the beach is the same as the distance home. So there is our equation. Now we substitute in what that distance represents, which is rate and time. Now those will change for each side of the equation, but still they make an equal expression so that we could use it to find an unknown, to squeeze out the relationship. So on the left-hand side, we have the rate to the beach and the time it took to get to the beach. On the right-hand side, we have the rate home and the time it took to get home. You could use subscripts of 1 and 2 for the left and right-hand sides of the equation respectively. But the lettering here with the subscripts with B and H for the left and right respectively help us know what we're doing. And this is a great way to set up and go step by step to solve the problem. So let's substitute on the left-hand side what's happening when Serena goes to the beach. So the rate is 3 hours, so that'll be our time. And it says she bikes 2 miles per hour faster on the way back. So it doesn't tell you how fast she biked there. It doesn't tell you how fast she biked back, just that she had biked faster. So that means the rate is going to remain the unknown throughout the problem. And you could see there in the end, the last prompt is that how fast did she bike when going to the beach? So with that being said, I'll substitute in the t. I will adjust the r to include that piece where it's 2 miles per hour faster, and then I'll solve the resulting equation. Let the algebra do the heavy lifting. So I'm just going to substitute in what I know. I don't know how it's going to shake out, but I know my algebraic steps to get me there. So I substitute in the following. 3 hours to the beach, that's time to the beach. And as I go through here, I'm not going to use the subscripts anymore because now we're including the values, and instead I'll just use that R value. So that's the left-hand side. On the right-hand side, we have a return trip of 2.5 hours. And for the rate, we're told that we go 2 miles per hour faster. So rate plus 2. And there's our equation. So notice we have variables on both sides. I have a 2.5 that I'd prefer not to keep in the problem because of the challenge that it will present with our arithmetic. So let's think about converting 2.5 to a improper fraction. So 2.5, first of all, as a mixed number is 2.5. That's an easy step to change it to. So I just looked at the decimal and what fraction equivalent it would be. And now I need to make that an improper fraction because mixed numbers are not conducive for algebra. So the way that you do this is you take the denominator and you multiply it by the 2, and then you add it with the numerator. So you get the following. So we have 2 times 2, or 4, and they'll be added to the numerator that's already there, and we keep the denominator unchanged. And so this simplifies to 5/2, and think about that. 2 evenly divides 5 twice with the remainder of 1, and 1 on 2 is the 0.5. So now that's the value I'll substitute in here, and so we could get on underway with the algebra. So rewriting the equation, I have 3r is equal to 5/2 times the quantity of r plus 2. Like we did in a previous problem, I don't want to distribute that fraction, so I'll multiply both sides by the denominator of 2. So on the left-hand side, we get the product of 2 and 3, which is 6r. And now that 2 simplifies out to 1. And so now we just have 5 outside the parentheses times the r plus 2. The left-hand side isn't a multiple of 5, so I will distribute that 5 to the right. So we get 6r equals 5r plus 10. And when we move the r to the left using its additive inverse of negative 5r, we're left with a single copy of r on the left, and it equals 10 on the right. And we need a unit because this is a real world context, and that is how fast did she bike going to the beach? And we need to think about our units. And so if we go to this formula, distance is equal to rate times time. The rate is right here, miles per hour. So MPH for short. And we could box that answer.